Okay, so we are going to start again. So I'm going to first maybe, in which order do I do it? No, first the proof, and then I will give you maybe the historical approach. I mean the physicist approach to this type of quantities, of theorem. So the proof. So take omega to be the space of pairs of percolation configuration and spin configurations, omega and sigma, sorry, such that for every edge in edge xy, omega e equal 1 implies sigma x equals sigma y. Okay, so I'm restricting myself to this type of pairs in the sense that they need to be compatible. So if the edge is open, then the two spins are the same. The spin at the endpoint are the same. So you note, for instance, you see that this construction is exactly enforcing that. So now if I look at the percolation measure, I mean the probability, sorry, of the pair omega sigma constructed like that, what do I get? Well, I need first to sample the percolation measure. So when omega 0, I will just denote it. Oh, I can put omega 0. That's the first thing. I need to sample that. And then I need to choose for every cluster one of the Q colors. Okay? So in order to recover exactly this sigma, for every cluster, I had probability 1 over Q. Right? So I get 1 over Q to the k of omega 0. So these two things cancel. And I recover something very simple, P of O of omega, 1 minus P of C of omega, and Z0 PQ of G. So it's not very complicated expression. Now, if I want to prove, so I know already, when I look at this P, I know already that the first marginal is the random cluster measure by construction. Now, let's try to define another measure for which I know automatically that the second marginal is the Potts model. So I'm going to start from sigma, and I'm going to do the following thing. If spins, so I take an edge E, and if sigma x is different from sigma y, I put omega E equals 0. I don't think. And if sigma x is equal to sigma y, so if the two endpoints of my edge have the same spin, then I choose omega E equal 1 with probability P and omega E equals 0 with probability 1 minus P. Okay, so if I don't have the same spins, I close. If I have the same spin, I choose according to a Bernoulli parameter P. So you notice that if my edge is open, then automatically sigma x equals sigma y. Okay, so I'm again in the space omega. Now, what is the measure, P tilde, that I obtained by doing that? Well, I need first to sample the first measure. So I have Z G beta 3, and I have an exponential of minus beta. And here, the way I'm going to write it is I'm going to write it beta Q over Q minus 1 times R of sigma, and R of sigma is the number of edges with sigma x not equal to sigma y, of edges E equal xy. Okay? This is just another way to write the Hamiltonian that we introduced for the Potts model. Okay? Let's not try to do it. It's exactly, I mean, trust me, exactly the Hamiltonian rewritten in terms of this R of sigma, of the number of points that are identical or not. I mean, that number of neighbors that have the same spin or not. And now I need to choose for the remaining edges if they are open or closed. So I'm going to have p to the number of open edges and 1 minus p to the number of closed edges. But the number of closed edges among the remaining edges. So the number is going to be the total number of edges minus the number of edges that I didn't look at anyway, minus O of omega. Okay? These are all the edges that remain. So I have the open edges, I have the edges that I didn't look at because they don't have the same spin, and these are the remaining edges. I need to pay a 1 minus p for each one of those. Now if, and that was what I assumed, 1 minus p is equal to e to the minus beta q over q minus 1, what do I get? I get that this cancels out with this. So I get that it's p to the number of open edges. Now it's 1 minus p to the number of edges minus the number of open edges. So it's 1 minus p to the number of closed edges. And I have the g beta free. And we deduce from that, therefore, what do we get? We get exactly the same measure as before. We get p to the number of, I mean, the probability of a configuration omega sigma is proportional to p to the number of open edges, 1 minus p to the number of closed edges. So this measure p tilde is just the measure p that I introduced before. But for the measure p, I know that the first marginal is the random cluster measure. For the measure p tilde, by definition, the second marginal is the Potts model. So that means that the coupling for the measure p itself, it's already that. So the first marginal is the random cluster. The second is the Potts model. I have a coupling between the two. OK? So this may be, I mean, at least for the physicists in the room, it's a little bit unorthodox somehow. It's not the way you do this type of connections between models usually. What you do, and I want just to do it as a side remark, is rather the following. So by the way, I mean, maybe, so one remark before, if I take wired boundary condition, I can do the same coupling, except on the boundary, all the clusters on the boundary, I don't choose uniformly their color, I choose it to be 1. Okay? And sigma c equal 1 if c intersects the boundary. Then, if omega is sample according to this guy, then, in fact, sigma is going to be sample according to the Potts model, but with boundary condition 1. So not free boundary condition, but boundary condition 1. So it's not restricted to the free boundary conditions. So that was something which is going to be important. And before, so I told you I want to do another remark, is from the perspective of physics. What usually you try to do is to get connections between the partition functions themselves. So you look, for instance, at the partition function of the Potts model. Okay? On a graph G, I'm going to, well, okay, on G and beta. So this is going to be what? It's going to be the sum for sigma in TQ of V of G of exponential of minus beta times the Hamiltonian. And you try to connect this guy to the random cluster measure, random cluster partition function. So how do you do that? Well, you can first do the following thing. Don't disregard this term. It's not very important, but this thing, you can rewrite it as a sum of a sigma of the product over the edges x and y. So these are edges of G of the following quantity. Let me just not make a mistake. E2 minus beta q over q minus 1 plus 1 minus e to the minus beta q over q minus 1 times indicators that sigma x is equal to sigma y. You can just check that because for every edge, the scalar product of sigma x and sigma y can take only two values, which is basically either 1 or minus 1 over q minus 1 over q minus 1. Then you can just rewrite this exponential as this product. There is just a normalization factor that arises. But now this, you can write it. Let's keep this guy here. You can write it as a sum over omega of a percolation configuration of p to the number of open edges, 1 minus p to the number of closed edges, and the sum of a sigma in tq of v of g of delta of sigma x equals sigma y, product of delta of sigma x equals sigma y for xy in the configuration omega. So what did I do? I need to explain a little bit that. First, I did something wrong. There must be a different here. No, sorry, that's equal. So what did I do? I just said here, when I expand this thing, either I take this term or I take this term. Okay? So with the notation that 1 minus p is e to the minus beta q over q minus 1, I get some p to the some power, some 1 minus p to some power. And what I decide is that every time for every edge, if I take this guy, I declare the edge closed. And if I take this guy, I declare the edge open. Okay? So it's the sum over every possible open-closed configuration, so every percolation configuration. Every time I take this, I'd say it's closed, so it gives me 1 minus p to the number of closed edges. This gives me p to the number of open edges. And this is just saying the open edges here are the edges for which sigma x equals sigma y. Okay? But now here, look at that. For a percolation configuration, what is this sum? Well, I want here, I need what? I need sigma x to be equal to sigma y for every vertices x and y which are in the same cluster. So for every cluster, I have one choice of sigma. So when I sum over everybody, I get q to the number of clusters. So here, I get this quantity and then the sum of omega, p to the number of open edges, 1 minus p to the number of closed edges, q to the number of clusters. So I recover exactly the partition function of the random cluster model. So that's how it was proved originally in physics, how it was discovered in physics. Now, what is the advantage? So here, basically, you get e to the beta e of g and z of p q g 0. So this is very good for people. I mean, I'm not going to do it because I'm maybe lacking a little bit of time. But here, if you take G to be the box of size n, and you let n tends to infinity, and you renormalize by 1 over, I mean, you take the log and you divide by the size of your box, what do you get? You get a connection between the free energy for the Potts model and the free energy for the random cluster model. So for a physicist here, you won't, because basically, the singularity of the Potts model, of the free energy of the Potts model, tells you how it behaves and how is the phase transition for the Potts model. But since the Potts model is directly related to, I mean, the free energy is directly directed to the free energy of the random cluster model, it tells you also how the phase transition of the random cluster model is behaving. So there is a connection between the two phase transitions through the free energy. The problem from a probabilistic point of view is that we want to know more than the information which is provided by the free energy. We want to really study the geometry of the model, and in order to study the geometry of the model, the coupling that I described is a much stronger tool. It's much more powerful. It gives you much more information. I'm going to give you a few examples afterward. And in particular, one thing which is troubling when you only look at the free energy is that, I mean, the reason why this thing was studied in physics later on is that the Potts model, you can do, I mean, in the planar case, usually what you do is, by the way, this works for any dimension, right? But if you restrict yourself to the planar case, studying the Potts model directly is difficult. But in fact, the random cluster model, the Fortune-Castle interpolation, is related to a nice type model, which is integrable at criticality. So in fact, I'm going to mention that next week, the free energy at criticality of the Potts model is equal to, I mean, is related to the free energy of this model at criticality, which itself is related to the free energy of this ice-type model, which you can compute. So you can compute the free energy of the Potts model. The problem is that you can compute it only at criticality. So it doesn't provide you any information, because if you want to study the phase transition, you need to study the thermodynamical quantities of your model, and they are derivatives of your free energy with respect to certain parameters. Okay? So you would need to have this connection for a larger range of parameters. So I would say that, at least from our perspective, this connection between the partition function is a little bit too weak. So we're going to really work with this quantity. Sorry for divaguing a little bit, but I think it's interesting to have at least the motivation underlying that. So speaking about what you can do, what are the consequences of this coupling, for instance, you can, provides you with a dictionary between the quantities of the different models. So if I look at this quantity, if I want to look at, let's take 3, at the spin-spin correlation of the Potts model. Okay, so I look how much two spins are aligned. Well, since I have my coupling, I can just write it as P of sigma x, sigma y. I can look at the average of this thing. But now I can, so this is an information which is only, it's only an information on the first marginal of my model. I can tell something about the second one. So I can say, well, let's put an additional indicator that x is connected to y in omega. And let's, of course, I cannot just put that. And so I'm going to put the complement here. So you agree, a priori, if I don't have that, it's exactly this thing. So I'm just dividing in two pieces whether x is connected to y or x is not connected to y in omega. But now, if x is connected to y, sigma x, by construction, has to be equal to sigma y. So this quantity is 1. Okay? So what do I get? I just get the probability that x is connected to y in omega. The second term now. If x and y are not connected, then sigma x and sigma y are chosen uniformly. Okay? So you choose sigma x, and sigma y is chosen uniformly. But the polyhedron is made in such a way that when you average over the spins, you get 0. So this quantity will give you 0. So you only get that, and now this is a quantity that depends only on the second coordinate. Sorry, I'm going to put it a little bit higher. So now I can just write, well, if it depends only on the second coordinate, it's just this quantity. So what did I get? Well, I exactly got a geometric representation as I defined last week. The spin-spin correlation of my Potts model gets rephrased in connectivity properties of my percolation model. model, sorry. Okay? So in particular, the phase transition are going to be related directly. So let me give you another example. If I look at this quantity, so if I look at how much the spin at x is aligned with 1, but I take 1 boundary conditions. Well, if I do the same thing, and I'm sure you will trust me on this one, that it's exactly the same line, I'm going to get that it's the probability for the random cluster model that x is connected to the boundary of the box. Because if it's not connected to the boundary of a box, it's in a cluster for which I chose uniformly the spin, so I get 0. If it's connected to the boundary, the spin is fixed to be 1 by construction of the coupling. But you see now, it provides information because, for instance, there, when you take G, when taking G to ZD, this thing tends to 0 if and only if this thing tends to 0. But this, you feel, I didn't tell you exactly what I will mean by infinite cluster, but you feel that this is going to be related to the existence of long-range interaction in this model. So the critical value of the Potts model is going to be related to the critical value that I'm going to define in a moment of the random cluster model. OK, so that was the coupling. And now so this motivates us now to define what we mean by the critical value of the random cluster model. Because as it stands now, we only define the model in finite volume. We don't have an infinite volume version of that. So before being able to define this infinite volume version, we are going to need to go through the basic properties of my random cluster model. And there, I'm going to just try to compare this to Bernoulli percolation. So this is third paragraph, something like that. So basic properties. So what did we have for percolation? We had monotonicity in P. So the larger the P, the more open edges we have. We had the FKG inequalities, the fact that for increasing events, the probability of the intersection is larger than the product of the probabilities. We had a differential inequality. I will maybe not mention it now. This Rousseau's formula, it was useful in our context. And, well, that's basically all. So let's try to see if we have equivalence there. So let's start by the FKG inequality. And as I said last week, the FKG inequality for Bernoulli percolation is called the Harris inequality. It was not proved by Fortuyn, Castellane, and Guénibre. But now you understand why it's called FKG, because in this context, it was proved by Fortuyn and Castellane. That's one of the first things they tried to prove, because that was one of the main, the first tool you need to grasp a little bit of the model. So the FKG inequality is going to work. But it's very funny. It's going to work. It's not funny at all. I don't know why I said that. It's strange, but it works only for Q larger or equal to 1. So the cluster weight has to be larger or equal to 1. In fact, for Q smaller than 1, it just fails. And you can guess that because when Q tends to 0, for those who want to think a little bit about this model, you can recover electrical networks, so uniform spanning trees and things like that. And these models are notoriously negatively correlated and not positively correlated. So, but for Q larger or equal to 1, we are going to have exactly what we want. So when I look at two increasing events, when I don't say P, G, or Xi, is that it works for any values. And we get exactly the product, the FKG inequality. So the proof is more complicated than in the context of Bernoulli percolation. I told you for Bernoulli percolation, just do an induction. It's a very easy exercise. For this model, it's more complicated. The proof is based on the Hawley criterion. well, I'm not going to describe it here. You can find it not in the notes, but in my book or in Jeffrey Grimet's book. The English is better in his book, definitely. OK, so this is the FKG inequality. Unfortunately, I cannot prove it. But now let's see, for instance, for the monotonicity. Monotonicity. So here, same thing is going to work for Q larger or equal to 1. So if I take P smaller than P prime and A increasing, I'm going to get exactly what I want, meaning that if I look at the probability of an increasing event, it's going to be smaller at P than at P prime. So this is really saying the larger the P, the more open edges you get. In fact, you even have a coupling, which is exactly telling you that. You can couple the two models in such a way that you have more open edges in the first one, in the second one than the first one. But we don't need that. We will only need this inequality. OK, and this one, in fact, I can prove to you from the Potts model, the FKG inequality, that this is true. Why? Because if I define y to be p prime 1 minus p over p 1 minus p prime to the number of open edges. So notice this is an increasing function, okay, because p prime is larger than p. So it's something positive to the number of open edges, something bigger than 1 to the number of open edges. And now you can notice that this thing is nothing but the indicator of A times y divided by the average of y. By the way, here when I say here I'm really taking the measure. I mean, this is the expectation of the random variable. Okay, I'm not doing like interpolation when I'm using p and e. Here I'm just denoting the expectation and the measure by the same thing. But now I have an increasing event and an increasing function and an increasing function, so I can use the FKG inequality, get that it's bigger than the product of the two. The expectation of y simplifies, and I just get this quantity. Okay, so this is just the FKG inequality. Once I have the FKG inequality, the monotony is following directly. Good. What else could I look at? Well, there is something that was not really present for percolation, is the boundary conditions. And there is a natural question, which is maybe you want to compare different boundary conditions. Okay? So comparison between boundary conditions. So if I take psi, which is smaller or equal to psi, and let's say, so Q is still larger or equal to 1, A is increasing. And this, I mean that there are more wirings in psi than in psi. Okay? So there are more open edges that are wired in psi than in xi. But well, what is going to happen is what? Is that if I look at the probability of an increasing event in my graph, the fact that there are more wirings outside is somehow pushing the configuration up. There are more open edges. So this thing is going to be smaller or equal to this quantity. So this may look like a useless property at first sight, but I'm going to give you two justifications in a row that this is a good thing to have such an inequality. The first one is that how can I compare this quantity? I mean, what is the smallest boundary condition possible? The one with the least number of wirings. Well, that's the free boundary condition. There are no wirings. So this quantity is always larger or equal to phi 0 PQG of A. On the other hand, what is the biggest one? Well, the biggest one is with everybody wired together. So it's the wired boundary condition. And I get that. So this is the first observation, is that somehow phi 0 and phi 1 are extremal in terms of boundary conditions. And the second observation comes from the fact that, well, at some point, we are going to need to have something to just go over independence. Before, for Bernoulli percolation, we had independence, very good for us. But now, once we are going to condition on an event, even if it doesn't depend on the set of edges of the other events, it's still going through dependencies to influence the probability of the other guy. So we need to understand how it does that. And there is a property called the domain Markov property, which is telling us exactly how it does that. So imagine I take a graph f included in G. Okay? And assume that x is, A is an event included in 0, 1 to the edges of F. So it's an event depending only on edges in F. Then assume as well that I give you psi, a configuration in 0, 1 to the edges of G minus the edges of F. So I'm telling you what is happening outside the graph of the graph F. Then what I have is that if I take the random cluster measure on G, but I look at the probability of the event A condition on the configuration omega E equal to psi E for every edge not in E of F. So if I tell you everything outside, what am I getting? Well, I'm getting exactly the probability on the event F, on the graph F, but with of A, but with boundary conditions psi psi. So what does it mean? It means that the boundary conditions inherited by, conditioning on the configuration outside are exactly the boundary condition of the configuration outside. So you notice that for Bernoulli percolation, it has no influence because Q equal to 1, so then the clusters have no influence there. But here, it's going to tell me, well, it has some influence. It's telling me something about what is going on, how is the probability of A computed. Why? Because it's telling me how I need to count the clusters inside. It's telling me the boundary conditions. But combined with the comparison between boundary conditions, you see that there are nice things that you can do. For instance, this quantity is always going to be smaller than that and always larger than that. So that's why this comparison between boundary conditions is useful, because we are going to condition on events depending somewhere and there say, OK, this is influencing what is happening at my place. But worst case scenario, it's like free boundary conditions. Best case scenario, it's like wired boundary conditions. And if I can treat these two cases, I'm done. So that's why these two things are very complementary and very useful. Just a small corollary of this thing, which is important, is if I look, if I condition about everything except the edge E, what is happening at the edge E, then for Bernoulli percolation, the probability of being open is just P, and close 1 minus P. Here, I want to say that whatever I'm conditioning on outside of my edge E, well, the probability of being open is not going to be P. But I want to say it's not, it cannot be too small and cannot be too big. And if you use this thing, just for A being the event that the edge E is open, you're going to easily see that, I mean, it's going to look at the probability for P, Q, and here you can just take F to be the graph given by just one edge. There are going to be boundary conditions, which are going to be either free or wired in this case. But you can compute in both cases and just see that whatever, so if you look at the probability P, Q, and G of omega E equal 1, knowing omega F for every F not equal to E, so I'm conditioning on everybody except that, then you can check easily that in fact it's larger than P over P plus 1 minus P times Q, and it's smaller than 1 minus that. So it doesn't tell me what it is equal to, but it's telling me, so 1 minus that is just 1 minus P Q over P plus 1 minus PQ. So this is, I mean, I don't know what this is equal to, but it's never too small, never too big. And this is going to be very important because in many places in the arguments we use for Bernoulli pair correlation, we use something like, OK, I'm looking at an event that depends on edges outside my box. So inside, it's independent, P to the number of edges. Here, it's not going to be independent, but every edge is still going to be open with probability at least P over P plus 1 minus PQ. And this is going to be sufficient for what we want. So this is called the finite energy property. There are models for which you don't have this type of property. And the typical example is, for instance, uniform spanning tree. There, I mean, if you condition on the state of edges outside, I mean, every edge except one edge, well, maybe you cannot open this edge, because otherwise it's going to create a cycle. Okay, so these models are not like that. These models, you have the finite energy property. If you want to open an edge, it costs you only finite factor in the energy. Very well, so these were the basic properties of the model. I didn't tell you how you get this comparison between boundary conditions. Well, in fact, you can use the FKG inequality. It's a small exercise. You can try to do it. It's not very difficult. Otherwise, you look in the notes. So basically, the only big thing I didn't prove is this FKG inequality. Here, by the way, this is straightforward. You can just check. It's absolutely straightforward. There is nothing hidden there. OK. So we get to the fourth point, which is the phase transition. What is happening for the phase transition? And already we have a difficulty because the phase transition occurs in infinite volume, and we only have defined our model on finite graphs. So the first step is, how do we define an infinite volume measure? Volume measure. So we cannot do it directly because there will be an infinite number of open and closed edges, infinite number of clusters, so the formula doesn't work, of course. And even it's unclear what we call an infinite volume measure. So I'm not going to tell you what we call an infinite volume measure here, just because it would not add much. But I'm just going to tell you that, I'm just going to explain how we construct two of them. OK? So we are going to do the following. We are going to construct them in terms of, as limits of finite volume measures. So theorems. So there exists, let Q larger or equal to 1, P in 0, 1. There exist two measures. I will call them phi 0 PQ and phi 1 PQ. They are measures on 0, 1 to the number to the edges of ZD. So they are percolation measure on ZD directly, such that for every event A depending on finitely many edges, what do I have? Well, I have that these measures are the limits of measure in finite volume in the following sense. So it's a weak limit of measures. So I have phi 1 pq of A is just the limit when n tends to infinity of phi 1 pq lambda n of A. And the same thing for the free boundary conditions. So this is the most natural thing you can try to do. You take finite volume measures, you take the limit, and you get that. By the way, you could just have, take any boundary condition, any sequence of measures with lambda n growing, and just extract a subsequential limit. But I want something quite, a little bit more explicit than that. OK, let's prove that. I'm going to do it for the free boundary conditions. The wired works the same. So let's take an event A, depending on edges in lambda capital N. And let's choose small n larger than capital N. And let's choose A increasing first. So what is happening when I compare this thing? Maybe let's drop the P and Q. Lambda n plus 1 of A, how can I compare it to this guy? Who is the biggest? Well, bonjour. Well, you see, this measure, since A depends only on edges in lambda n, what you can do, you can condition on every edge which is not in lambda n. So then, by the domain Markov property, you get a certain boundary condition, random boundary condition, on the boundary of lambda n. But this boundary condition is always bigger than the free boundary condition. So this guy is always going to be bigger or equal to that. So I have an increasing sequence of numbers, okay, real numbers, bounded by 1, so it converges. So this thing converges to a quantity which I can call phi 0 of A. Now, by inclusion-exclusion, so this defined to me an object on increasing events. By inclusion-exclusion, I can define this for any event depending on finitely many edges. So I need to check that I'm always going to get something coherent. But this is just due to the fact that the object I'm starting with are measures. So the coherence in the measures is going to give me the coherence in this object. So this defines to me a phi 0 directly on finitely many edges. And since anyway the sigma algebra is the sigma algebra generated by the events depending on finitely many edges, I get my measure on everybody. OK? So this, and for free boundary condition, would be for wired boundary condition, it will give you a decreasing sequence of measures. So you get two measures, and I really want to highlight the fact that there is absolutely no reason, and it will not be true in general, that these measures are the same. Okay? But still, they play a very special role. So let me just state without proofs a few facts about these measures. The first one is phi 0 pq and phi 1 pq. They are translational invariant. This you can check. It's an easy exercise. So they are translational invariant. And they are also ergodic. So at least, you define two measures in infinite volume. But, they are ergodic, so they are somehow extremal in some sense. because as soon as you define the infinite volume measures, you can define a convex combination of them. So if they are different, you can easily define non-ergodic infinite volume measures. These ones are ergodic. What else do I want to say about them? I definitely want... Oh, so they are really extremal in the sense... Well, this is going to be a little bit empty statement, but for any infinite volume measure, I didn't tell you exactly what is an infinite volume measure. So, but there is a natural notion of increasing of infinite volume measure, and in particular, they are all sandwiched between the free and the wired. So this you have to trust me on this one. And in particular, this implies that if phi 0 pq is equal to phi 1 pq, then there exists a unique infinite volume measure. Okay, so these measures, they are somehow good witnesses of the how rich you can do in terms of constructing infinite volume measures. By the way, in dimension 2, so maybe just think of these as being the infinite volume measure. In dimension 2, the only possible infinite volume measure are the convex combination of these two measures. In dimension 3 and more, you can get more complicated measures by using Dobryshin boundary conditions, but I don't want to provide more details here. And the last thing that I want to say, so this was the first fact, this is the second fact. The third one is that, in fact, by studying the free energy of the model, you can prove that non-uniqueness points are very rare. In fact, values of P such that, so you fix Q, values of P such that phi 0 PQ is not equal to phi 1 PQ, so they are the values of P for which you don't have uniqueness, it's at most countable. Form a countable set. I mean, at most countable, I mean, depends how you define countable. In fact, we will see that in dimension 2, it's either empty, so there is always a unique, or it's one point and it's a critical point. So it's here. So when I say you use the free energy, basically the free energy is a convex function, and the point of discontinuity are the only points where you can have non-uniqueness. The points where it's not differentiable. Sorry. Okay, well, we are getting to our points. So now we can define. So, and yes, and the last remark, but it's a trivial one, all the properties I described, they still work for the infinite volume measures, the FKG inequality, the monotonicity, these things. So basic properties, they get to infinite volume. Okay, so now the next theorem is the following, that there exists PC, which is a PC of D, such that for every P smaller than PC, and every infinite volume measure, there is no infinite cluster almost surely. Well, let's put this infinite cluster. And for every P larger than PC, phi PQ of there exists an infinite cluster is going to be 1. So here I really mean any infinite volume measure, so in particular phi 0 or phi 1. Sorry? Yes, PC depends also on Q. I should have written that. And oh, I should really define something. Sorry. That's the habits of only working with. So first, that's a very good point that it depends on Q, and very, very important. I mean, this construction that I define here works only for Q larger or equal to 1. Okay? So very good question. Okay, let me prove that and state last theorem, and I release you for this week. So let's prove that. So, I mean, PC, you can just define it as the infimum of the P for which phi 0 PQ of the exists infinite cluster is positive. Right? That defines me a PC. It's well defined because this is an increasing event, so the monotonicity property tells you that this, this is well defined, period. Now, what you know is that for P larger than PC, this guy has to be bigger than 0 because of monotonicity. But because of ergodicity, then it has to be equal to 1. There is no choice. And because this is the smallest of the infinite volume measures, it works for any infinite volume measure. Now, if I fix P smaller than PC, what can I do? Well, I can say that phi 0 PQ of there exists an infinite cluster is 0. Good for me. But that doesn't imply directly that it's true for any infinite volume measure. It could be that phi 1 would have an infinite volume, an infinite cluster. So how do I do this? Well, between P and PC, because the set of P's for which there is non-uniqueness is countable, there must be a point in between where I have uniqueness. So I need to have, there exists a P0 between P and PC such that phi 0, so now such that uniqueness, sorry. And now what I can say is that if I look at there exists infinite cluster, well, this is definitely smaller. So for any infinite volume measure, it's smaller than the quantity for wired boundary condition, because that's the biggest one. But now this guy is smaller than phi 1 P0Q, just by monotonicity. But at P0, this guy is the same as the free boundary condition. So this is the same as phi 0 P0Q. But since P0 is strictly smaller than PC, it gives me 0. So you see here in this theorem, I really want, somehow you could have defined a PC for the free boundary conditions. You could have defined a PC for the wired boundary conditions. And a priori, there would be no reason they would be equal. But since I have uniqueness for all but contably many values of P, I deduce that these two PC are the same. So there is really a sharp phase transition between the two. So now I have a PC, and in particular, beta critical of Q, so the critical value of the Potts model is going to be equal, times the log of 1 minus PC of Q D. And here I should maybe put a D as well. So now I have indeed that the critical value of the random cluster model and the Potts model are related. And in particular, I had something that I told you that the spin-spin correlation for the Potts model were positive. At some point, I told you that. And I said, I look at the order parameter, it's positive, and so on. Well, a priori, it was not obvious. But now, since I have the relation with the random cluster model, it becomes obvious because it's just a probability that there is an infinite cluster. That, the average spin at 0 is just a probability that 0 is on the infinite cluster. So you see, for free, somehow almost for free, if free means 2 hours of your time, you get the positivity of the thing. So that's one of, so this quantity, which was the limit and infinity of lambda n beta 1 of this guy, is going to be just phi 1 of pq of 0 connected to infinity. So in particular, it's positive it's positive or equal, and in particular, depending on whether you are below or above PC, it's strictly positive. So let me just state the last theorem, and like that, you can think about it and try to prove it for next time. It took me much more than 2 weeks to do it, so I will be a little bit annoyed if you do it in 2 weeks, but I will be happy for you. Try to be happy for you. So the last theorem is, so exactly like for percolation PC equal 1/2 on Z2, what can you do on Z2? So computation of PC on Z2. And so that's a theorem by myself and Vincent Beffara. And it says the following. For Q larger or equal to 1, I can define PC of Q and 2, and this is just square root of Q over 1 plus square root of Q. And next week, I will explain to you why it's natural to predict this. I will not prove the theorem because it's a little bit too long, but I will at least give you ideas. And for those who want to try to at least guess why this is a value, you can try to see if there is a notion of duality for this model, which will be an extension of the duality for the percolation model. See that square root of Q over 1 plus square root of Q is the self-dual point, and try to see whether at least Zhang's argument works. And see that, well, to prove exponential decay, it's a little bit more complicated, but that if you manage to do it, you are done. And you notice that for Q equal 1, you get 1/2, so Kesten is OK with this theorem. And I will see you in 2 weeks, I hope, at the same time. Thank you very much.